In this video, we'll introduce the direct comparison test and the limit comparison test. Up first, with the direct comparison test, we suppose that the series a sub n and b sub n have positive terms. And what we want to do is we want to compare a series, say a sub n, with another series that we already know something about. So b sub n is going to be a series that we know either converges or diverges. So it should be familiar. It's going to be either a p-series or a geometric series or maybe the harmonic series. Whatever the case, we know something about it. If b sub n is convergent and a sub n is less than b sub n for all n, then we can say that the series a sub n is also convergent. Let's get a quick visual just to kind of see what's happening there. Again, b sub n is the one we know a little bit about. So let's say b sub n we know is going to be convergent. So it looks something like this. We know it's bounded by the x-axis because it's got to be positive terms. So b sub n is up here and it's converging. And we know that a sub n is below b sub n. So let's say a sub n is somewhere down here. Again, a sub n is less than b sub n for all values of n. If b sub n is convergent and a sub n is less than b sub n, then by comparing those, we can say that a sub n is also convergent. Similarly, if b sub n, again, we know a little bit about, and it is diverging, and a sub n is bigger than b sub n, then a sub n is going to have to diverge as well. For example, let's use the direct comparison test to show that the first series converges by comparing it to the second series. So this time I'm giving you the two series. You're not always going to be given both of them. You typically have to create the second one to compare with the initial. So starting with the initial, n divided by n cubed plus 5. First of all of those terms need to be positive. And we can see that's going to happen if n is starting at 2. Then every value for n is going to spit out a positive value. And we can say that it is less than, what happens if we just remove the 5 from the denominator? If we remove the 5, the denominator is getting smaller. If the denominator is getting smaller, the fraction is getting bigger. So I can say with confidence that this fraction is smaller than this fraction because we made the denominator smaller. And now let's reduce the n's. This is 1 divided by n squared. So we have this fraction less than this fraction, and that's going to be for all values of n greater than or equal to 2, since we're starting our series at 2. And with this, we know something about this. The sum from n equals 2 to infinity of 1 divided by n squared is a p-series, right? It's going to converge because p is equal to 2, and that's greater than 1. And we know that when p is bigger than 1 for the p-series, we have a convergent series. So that tells us that the original sum, n equals 2 to infinity, that series must be convergent. This converges. In this example, we again want to use the direct comparison test to show that the first series diverges by comparing it to the second series. Again, you're not always told whether or not it converges or diverges. You're not always given the second series. Right now, we're just practicing what we have. N squared plus n divided by n cubed minus 2. We eventually want to compare it to this series, or just looking at 1 over n, the fraction. Let's see what happens if we remove n from the numerator. Removing n from the numerator is going to make the numerator smaller, which means the fraction gets smaller. So we can say that the first one is greater than the second one. Next, let's look at the denominator. If we remove the negative 2 from the denominator, and we simply have n squared divided by n cubed. If we remove the minus 2 from the denominator, the fraction again is getting smaller. And now we can reduce to get 1 divided by n, which is kind of what we wanted here. We wanted to compare it to the series 1 divided by n. We know that this, the sum from n equals 2 to infinity of 1 over n, diverges. Right, this is the harmonic series. We could also think of it as the p series. P equals 1, and if p is 1, it diverges. And since this diverges, and we're looking at a series that is actually bigger than this one, then the original series, n equals 2 to infinity, n squared plus n divided by n cubed minus 2, this must diverge. Up next, we have the limit comparison test. Sometimes direct comparison doesn't always work, and we need a different test. The limit comparison test, suppose the series a sub n and b sub n are again positive terms, and if the limit as n approaches infinity of their ratio is a constant, in other words, the limit exists, where c is just a number bigger than 0, then either the series both converge or they both diverge. For example, let's compare these two and show that they do converge by using the limit comparison test. We'll let a sub n be the first sequence, and b sub n will be our second, 1 divided by n squared. Now we'll take the limit as n approaches infinity of a sub n divided by b sub n. Limit n approaches infinity of n divided by n cubed minus 5. And we want to divide that by the b sub n. Dividing by this fraction is the same thing as multiplying by the reciprocal. So we can multiply by n squared over 1. This will give us the limit as n approaches infinity of n cubed divided by n cubed minus 5. Now recall the trick for limits at infinity. We'll divide by the highest power of n that occurs in the denominator. So we'll divide top and bottom by n cubed. We now have the limit as n approaches infinity of 1 divided by 1 minus 5 divided by n cubed. Here n is getting really big, n's going to infinity, so this fraction is going to 0, meaning we have 1 divided by 1 minus 0, or 1. Note that this is greater than 0. And recall, we know a little bit about this second series that we were comparing the original to. Since the sum from n equals 2 to infinity of 1 over n squared is a p-series, it's actually a partial p-series, since we're not starting at 1, but we can still start at 2, that's okay. So p-series with p equal to 2, which is greater than 1. We know that that means this one converges. And if one of those converges, and if the limit of the ratio is positive, and we know that one of those series converges, then they both must converge. So we know the sum n equals 2 to infinity, n divided by n cubed minus 5 must be convergent. It converges due to the limit comparison test. In our next example, we again want to use the limit comparison test to show that the first series this time diverges by comparing it to the second series. Notice that the second series we know a little bit about. It's the harmonic series, or part of the harmonic series, or we could think of it as a p-series, and it is divergent. So if it's divergent and we compare it with the first one using a ratio and a limit, if that limit is greater than 0, we can say they both are divergent. So limits n is approaching infinity, and we'll call this piece a sub n and this part b sub n. A sub n divided by b sub n. That is the limit as n approaches infinity of n squared minus n divided by n cubed plus 2. And we're going to divide that by this fraction, or multiply by the reciprocal, n over 1. Here we get the limit as n approaches infinity, n cubed minus n squared divided by n cubed plus 2. Let's divide both the numerator and denominator by n cubed. Again, we want to divide by the highest power of n that occurs in the denominator. Limit n approaches infinity of 1 minus 1 over n divided by 1 plus 2 divided by n cubed. Evaluating the limit now, we get 1 minus 0 divided by 1 plus 0. That is equal to 1, which is a positive value. So the limit is greater than 0. If that's true, then the two initial series either both converge or they both diverge. Since we know that this one is, the second one is divergent, because it's a p-series or a partial harmonic series, then the first one, the initial, must also be divergent. Due to the limit comparison test.